So just returning back to these series questions, rather than just number patterns, and I'll say practical in inverted commas, some practical questions of where we can use series and sequences, because of course I know this is a situation that a lot of people do. 2007 HSC, Heather decides to swim every day to improve her fitness level. Right? And so on the first day, remember, she's going to improve her fitness level. So the first time she does it, I'll just swim 750 metres. That's pretty easy to do if you haven't been doing any swimming. So that's on day one. And then every other day, let's add another couple of laps of the pool. So 100 metres. Now, just in case you weren't sure, they like to help you out in the HSC, you see. Just in case, that means then she swims 850. That would be 100 more. And then 950 and so on and so on. So write down a formula for the distance she swims on missing a T, nth day. Alright, so it really is. We just got to pull out the data. I guess that's it. So the first term is the 750 metres. Common difference, well, every day is 100 metres. We have our general term, A plus n minus 1d, subbing it in, and we come up with a formula. So it's really no different. It's just being able to pull the data out of the question. Well, how far will she swim on the 10th day? Well, now that we have our formula, we'll just sub in 10. Oh, there we go. 1,650. By the way, for those that are unsure, the longest Olympic swimming event in a pool is 1,500 metres. It takes about 15 minutes for the really good ones to do it. So, but she'll swim 1,650 metres. Well, how much would she have done over the first 10 days? Well, now that would be the sum of all the terms. So we want the sum of 10. Subbing that in. That's 12 kilometres. 12 kilometres. Of course, another way you could have done that is you could have used the A plus L formula. It worked out how much she swam on the last day, which was the 1,650, which we got in the last part. And, surprise, surprise, we get the same answer. Now, and again, a problem I'm sure we're all familiar with. Well, I wonder how many days it would take me to swim the equal of the width of the English Channel, which is 34 kilometres. I'm sure you've thought of the same problem. So again, sum to n, but this time we know what the answer is, but we want to know what n is. So when we rearrange this, we should end up with a quadratic, I would imagine. Yeah, there we go. Well, fortunately, everything will divide by 100. That'll make it a little bit easier. Okay, it multiplies together to give negative 680, adds together to give 14.
34 and 20. Yeah.
34 and 20. Or 34 and negative 20. Excuse me. Two possibilities, negative 34 or 20. Well, for this question, there's only one that makes logical sense. Mind you, if you thought about it and if you were feeling lazy, the negative 34 is a better answer. Because then it says, how many days to swim the equal of that? I can say, I did that 34 days ago. All right, let's have a look at another. So a company's sales are declining by 6% every year. We know that 50,000 items have been sold in the year 2001. During which year will the sales first fall below 2,000? So first term, 50,000. This is going to be a geometric sequence. The thing we've got to be careful with here, if it's declining by 6%, the ratio is not 6%, the ratio is actually 0.94 because we're decreasing by 6%, so each year is then 94% of the previous year. So we want to know when's our general term going to be less than 20,000. So general term, of course, A r to the n minus 1. There's our little inequality to solve. Let's divide that. Okay. Well, this is where we can take advantage of logs. I moved the n to the left-hand side because I'd like the pronumeral to be on the left. Log both sides, which means write down the word log on both sides. That allows you to use your log laws, bring the n minus 1 out the front. We now will divide by log of 0.94, but remember, that's a negative number. A log of a number smaller than 1 is negative. So if we change the sign, we change the sign. So it becomes a greater than. And when we sub it in, which log button do we use? Doesn't matter, as long as you're consistent. And add 1. So we want to know during which year. So n has to be greater than 15.8. So I guess that makes it the 16th year, doesn't it? It'll be sometime during that year. And just for completeness, I said, oh, by the way, that would be 2016. Another HSC one. Anne and Kay, employed by an accounting firm, and has conditions where I'll start on $50,000, and then in each year you can give me $2,500 more. Kay also starts with $50,000, but she goes, no. Instead of giving me $2,500 each year, you just increase it by 4% each year. Who is the smarter person? All right, well, the first one is an arithmetic sequence, so 50,000, common difference 2,500. Second one with geometric, but again, the ratio is not 4%. If we're increasing by 4%, so it's 104% or 1.04. So what is Anne's salary in the 13th year? Well, there's our general term. Sub in. And she's up to $80,000 in the 13th year. Okay. Well, no surprise for what the second question I asked then. Oh, well, what about Kay? Was her deal better or not? AR to the n minus 1. Oh, yeah. Kills it. Extra $51. I only had to wait for 13 years, but she got there. She beat her. She's going to keep it. Okay. By what amount does the total amount paid to Kay in the first 20 years exceed the amount paid to Anne in the first 20 years? Okay, so now we're dealing with sum. So Anne's an arithmetic. We'll use the arithmetic formula. Subbing in, all up, she gets $1,475,000. Kay, geometric formula. She gets 14 million. No, sorry, not 14 million. Oh, that'd be all right, wouldn't it? 1,488,903. Maybe she took on the CEO of a bank or something. So she gets an extra, almost $14,000 there. That's $14,000. I guess this one's not actually a practical problem, but I just throw it in there. Find the limiting sum of the geometric series. Now you notice this one, and this is a 2-unit paper, and it was right at the start, it was before the days of multiple choice. Question 1D, so a relatively straightforward one you'd think for 2-unit. So A is 3/4, the ratio is 1/4. Sum to infinity, A on 1 minus R, subbing in, and it's just 1. Nice quick one for that. Okay. Now, as opposed to the one in 2003, which was question 7, where they then said, yes, it's the same question, just a more interesting ratio there. So the first term is 2. The ratio, well, if you can't see it straight away, we can work it out by getting one term and dividing it by the other one. It's 1 on root 2 plus 1 is the ratio. Now, of course, we need to make sure that that is less than 1, and it is. So that's okay. So sum to infinity, summing it in, 2 over 1 minus 1 on root 2 plus 1. Okay, I've inverted and multiplied. Still got nothing here, right? Substitute in. Bit of mucking about. A little bit tricky, again, for a 2-unit question. A little bit tricky there. So 2 plus root 2 for that one. And they love this sort of one. Explain why, so that's when it was plus 1. Explain why this one does not have a limiting sum. And this is the sort of question where they're just checking that you know your definitions and what have you. So it will come down to be the ratio, basically. So we know it'll only have a ratio only have a limiting sum if the ratio is between minus 1 and 1. Our ratio is 1 on the square root of 2 minus 1. Now that's going to be bigger than 1 because root 2, of course, is around about, 1.44, something like that, isn't it? Yeah. And so subtract 1, you're going to have 1 over 0.4. Well, that's going to be bigger than 1. Oh, there you go. Turns out to be 2.414. So no good. And then, then this one. Consider the series. 1 minus tan squared plus tan to the power of 4. And it's alternating signs as well. Oh. Okay, let's consider it. A is 1. The ratio is minus tan squared theta. Okay, so when the limiting sum exists, find its value, because it's not always going to exist for this particular one. Okay, well, it'll be A on 1 minus R. So that's 1 on 1 plus tan squared. Hang on. This is a trig identity question. It's hidden in a series question. Because 1 plus tan squared is, of course, sec squared. Reciprocal of sec is cos squared theta would be the limiting sum of this one, if it exists. So that's why in the next part they've restricted theta to be in between pi on 2 and pi on 2. Because remember, the ratio was tan squared, or minus tan squared theta. But the tan of 90 is undefined. So for a start, we're going to have to restrict that. But also, if that ratio gets bigger than 1, we're going to have a problem too. Tan of 45 would be our spot. So anyway, that's, I guess, what we've got to find. So limiting sum will only occur when the ratio is in between minus 1 and 1. So minus tan squared theta has to be in between minus 1 and 1. Which means, well, if I change the sign, I change the sign. But that's ugly. Oh, it's the same thing. What do you know? But I guess that makes sense. I mean, if minus tan squared's in between minus 1 and 1, well, tan squared's got to be in between minus 1 and 1 as well. Which means tan is going to be in between minus 1 and 1. Now, we know that tan is equal to plus or minus 1 at 45 degrees. Notice I'm using radians here, because in the HSC, they tend to work with radians rather than degrees. So I drew a graph. Said, hey, look, here's my graph. Nice graph. 1 minus 1. Oh, look.
It curves back out.
Oh, look. No, it doesn't. It's your imagination, okay? So I know those x values, which of course are minus pi and 4 and pi and 4. So the limiting sum will only exist if theta is in between minus 45 and 45 degrees. What a nasty question for theta. Alrighty. So I just picked a handful of questions. That's in the second book, I think, by the way.